Thanks for coming to our SCiMMA Public Telecon. Today, Deep Chatterjee of the National Center for Supercomputing Applications will present on behalf of himself and Gautham Narayan and others a filter for electromagnetic counterpart identification during EM follow-up. And Deep and Gautham have been working in SCiMMA, bringing their machine learning and filtering expertise. So I'm looking forward to hearing this. During this talk, it's being recorded, as I think was probably announced when you join, and it will end up on YouTube. And if you want to raise your hand to ask a question, I will keep my eye on the hands, and I can just sort of break in and point it out to Deep at a convenient time. I'll also watch the chat as well.
Sounds good.
So take it away, Deep.
Thank you, Adam. Thank you for letting me talk here at the SCiMMA Public Talk. So as Adam mentioned, I'm a postdoc at the Center for Astrophysical Surveys at University of Illinois Urbana-Champaign. And today I'll talk about some recent work that we've been doing to get a filter, to build a filter for electromagnetic counterpart identification during follow-up of gravitational waves. So I'll start with some introduction. So as we all know that 03, the EMGW campaign suffered a setback after the third observing run from LIGO Virgo. It was a very successful run from the gravitational wave standpoint, but then from the EMGW standpoint, there were no counterparts that were detected. This was also the first time when the gravitational wave alerts went public. There was infrastructure set up to deliver them in near real time. And a total of 80 public alerts were sent. 56 of them stayed non-retracted. And as of today, the first half of 03 data has been analyzed, and it's available publicly. And there are quite a few candidates that have been discovered. So just for comparison, between O2 and 03. 02 was the first time when there was an EM follow-up campaign that was set up. It was not public though, but a total of 14 alerts were sent out back in 02, and only 6 of them stayed non-retracted and made its way into the GWTC1 catalog. And among which among those candidates, one of which was GW170817, which we all know. And during 03, there were several interesting candidates like GW190425, which is the binary neutron star, the heavy binary neutron star candidate. Actually, that's the sky localization, very sharp contrast with compared to GW170817. Then there was 190814, which is the very asymmetric mass ratio system with a 2.6 solar mass secondary object that also received a pretty good amount of follow-up. But unfortunately, even after four years, GW170817 still remains the sole success story of EMGW astronomy. And just to highlight some of the challenges that were faced during 03, I thought I would pick out this figure from a nice article by Michael Coughlin. So here on the y-axis, I have the luminosity distance, and then the size of these bubbles represent the sky localization. It's inversely proportional to the sky localization. So the larger, the better. And what immediately stands out is that GW170817 was an outlier in terms of distance. It was much closer and therefore probably not much of a challenge. Whereas if you notice a candidate like 190425, the binary neutron star, it's at 150 megaparsecs, and it has sky localization that was several thousand square degrees. And the interesting events that are all annotated over here, one thing we notice right away is that they are at larger distances, or they have very large sky areas, or it's a combination of both. And both those are, they make it difficult for following up for the counterpart. And added to that, there was other issues, like there was a lack of coordinated strategies to follow up. There was observations that were repeated by different teams. And so all of those contributed to some of the challenges in 03, and really maybe the needle in a haystack nature of the problem is starting to show up now. So in terms of future needs, there is promise because we'll have more sensitive surveys, both on the gravitational wave side and also on the electromagnetic side. But what that also means is that along with increasing number of candidates, we will have more impurity that we'll have to deal with. And therefore, open data sharing, rapid communication platforms, all of which are very important going ahead for the success of multi-messenger astronomy. And just to highlight on that filtering aspect, I just thought I would just pick out some of the snippets of the GCNs that were sent around following the discovery of some of the candidates. So here, for example, I have one of the GCNs reporting candidates from the Zwicky transient facility following the discovery of this candidate S200105AE, which had an initial interesting classification. There was a high chance of having a neutron star component. And then here we notice that several candidates were reported, but almost after about 3 days, there was spectra taken, and most of these were ruled out from the spectra as being different types of supernovae, like type 1a, type 2b, type 1b, and so on. And this is not a single incident. This actually happened more than once. Here is another one, 1908 14BV, which was very well localized, even better than GW 170817. Even in this case, we noticed that there were several candidates. I pick out this example where there are these DE-CAM candidates that were reported, but after about 10 days, these were categorized as different types of supernovae, type 2 for this one, stripped envelope supernovae, and some other types. So this goes on to show that as we go ahead, there would be more detection, there will be more events like these. We will be facing the same scenario, and we will not be able to take a spectra for each of the interesting candidates that we potentially see. So therefore, photometric classification will be very crucial in the future. And like I said, that's because we will have more sensitive gravitational wave detectors, so we find more candidates, more sensitive telescopes, which means more events, but at the same time, we will be overwhelmed by misclassifications and false alarms. So it's not hard to see a scenario where you have a situation like this, where a gravitational wave alert has been sent by the LBK, and then there is a true Kironova, which is shown in this red cross over here. It coincides with the high confidence region of the sky map. But then there are these other objects shown by these little blue crosses that are nearby, and some of them in pretty high confidence region on the sky map as well. And this will become very routine going ahead. So we need to filter the true Kironova out from the others from very early photometric data, or at least provide a filter so that we can downsize the number of candidates for which we spend resources like spectra. And so there is one work I do want to mention, and that is this code base called RAPID. RAPID is a photometric classifier, which is based on neural networks. Now, the use of machine learning has become pretty popular in photometric classification over the last decade. And the primary use case has been supernova classification. And that is because, of course, there are many supernova that is detected by surveys today. But then majority of these algorithms actually they expect full phase information. So in other words, the complete light curve of the transient. So if you give it a full supernova light curve, it will be able to tell you whether, what type of supernova it is. But then RAPID is different in that sense. RAPID was developed by Daniel Muthukrishna, who is a student of Gautham Narayan and Casey Mandel. And it is different from these algorithms in a sense that it gives predictions as the data is coming in. So here is an example. You have type 1a supernova. And so as the data flows in, there is a common pre-explosion class, which is high before the peak time of the transient. And then once that is passed. That is correct actually. And so once the explosion has happened, the correct class goes up. And so Rapid provides predictions as the data is coming in. And to do this, the network that was used was gated recurrent units. And one thing to mention in addition is that if in addition to the photometric data, if there is some other information that is supplied, some contextual information like the redshift, then the performance of the classifier goes up significantly. So something that sort of tells the classifier what this transient class could be. Okay, so before I tell more about plastic, before I tell more about Rapid, I wanted to mention briefly about plastic. So this plastic was a public challenge that was it was a challenge hosted on Kaggle in 2018 that aimed at classifying large data sets of light curves photometrically, and received pretty good amount of participation. And here are some of the model light curves that were used for plastic. And so plastic focused on LSST. There were different types of transient classes, and it generated this enormous data set that is now publicly available. And the reason why I mention this is because Rapid was trained on a subset of these light curves that were made available for plastic. So Rapid was trained on about 50K labeled light curves used for training, which involved both galactic and extragalactic objects. So objects like supernova, tidal disruption events, calcium-rich transients, superluminous supernovae, and in the galactic class, AGNs, Lyrays, M-dwarf flares, and such. And because it predicts classification in real time, you have this kind of confusion matrix, which evolves as more data comes in. So here is an example of the confusion matrix at the 2-day mark, where some of them are classified pretty well, but then as more data comes in, the classification score goes up. And as I've mentioned, that the original Rapid architecture used gated recurrent units. And I also wanted to mention some of the other photometric efforts like SuperNova and VRing for supernova classification and for anomaly detection. Now, the challenge with photometrically classifying Kironova is that the evolution is fast, the data is sparse, and oftentimes not enough to really do a good job with just photometric classification. So for example, over here, I have the GW170817 data. This is the photometry, this is the data from DECam. And if I just take this photometric data and just use stock Rapid, give it only this photometry, then what we see is that the classification is not very guided in a sense. All of the classes start out at a probability of about 1/10 because there are 10 classes. And then the Kironova class, which is this represented by the solid curve, I've only taken the first week of data. It actually does not do a very good job at classifying the light curve. Now, this is when we use a model that is trained on photometry only. However, if we train a classifier that uses both photometry and some other information like the redshift, and that's where the contextual information comes in, then we notice that there is an initial, just because we know the redshift of the host galaxy to be 0.01, we know the redshift of GW170817. The classifier is much well guided, and we get a better performance compared to what we would have with the photometric data only. And by the way, I just want to mention that I have not trained any of these models. This is just the stock Rapid code that is available publicly. Now, the challenge, however, is that redshift information that I just mentioned is not available during discovery. The standard image differencing pipeline does not provide you with a redshift. So we need some other contextual information. And we do have that in the form of the gravitational wave sky map. There is the, so this is just, we have a probability in RANDEC, and we have a sky location of the objects that we find. And so like things like that could be used as contextual information, things like the line of sight probability, the angular offset from the mode of the sky map, all of which could be used as contextual information to actually guide the classifier towards filtering out other transients. And so that is where LSID comes in, which is a variant of Rapid, where we are trying to solve a slightly simpler problem, in a sense of we are not trying to classify all different light curve types, but we are only trying to separate out Kironova from the other transient classes, so that it provides a preliminary filter to filter out, to narrow down on the candidates on which we would like to spend resources like spectra on. So what we want here is that mock sky map once again, and here the red cross would be the Kironova. It's at a high confidence region. So we want something that learns from the fact that there is, it is in a high confidence region, and at the same time it uses the photometric information to predict the Kironova class. But at the same time, if there is a different object, in this case a type 1ax, that is going on also in a high confidence region, well, initially the classifier would think, as we would all do, that it can be associated. It can be a Kironova, it can be associated with the gravitational wave, but then from the photometric information that comes in over the next few hours to next few days, it will quickly remove that possibility. And so we have to work with simulated light curves because there is only one real data point that we have thus far. And to do that, we rely on the supernova analysis library called SCiMMA. Now, SCiMMA has been around for almost a decade now, probably more than a decade. And it has several rules. Some of them are light curve fitting. It provides tools to do supernova cosmology. But the role that we are interested in is simulating explosive and variable transients. So what SCiMMA can do, if you give it a spectral energy density model or an empirical model like SALT2 for type 1a supernova, it can produce, it can propagate the flux taking into account host galaxy extinction, the Milky Way dust, take into account the observing schedule of a particular survey, its efficiency function, detection efficiency, magnitude errors, and provide a realistic simulated light curve. And this is the tool that was used to produce the order million simulated transients and variables that were used for the plastic public challenge. And naturally, the same tool has also been used in training Rapid that I talked about a couple of slides back. So we also use SCiMMA for our work. We use a survey, an observing schedule based on the publicly available ZTF DR3 data release. We incorporate the Kironova models into SCiMMA. And so by this, we are able to generate both Kironova and other types of transients like type 1As, core collapse supernovae, superluminous supernovae, tidal disruption events, everything using the same, a particular survey observing schedule. And so I wanted to talk about the Kironova models a little bit. So we are using the Kironova model grid by Mattia Bulla, which has also been used later in the literature by Dhawan and Michael Coughlin for their work. So this is a parameterized SCD model. The data is available on GitHub. And so this is an SCD model that simulates binary neutron stars, neutron star, black hole mergers. We only use the binary neutron stars over here. And it's parameterized by the ejecta mass, the half opening angle of the lanthanide rich component, and the observing angle. So the viewing angle, if it's face on or edge on. And here's an example of a Kironova light curve from a representative model. So the standard features are that the blue bands peak quicker and they decay fast. The redder bands, they peak later and are more brighter depending on the lanthanide fraction, and they last longer. So we have incorporated this into SCiMMA. And the data is now publicly available as SN data, as SNANA package data. And that is something that we use. I'm also showing over here the detected distribution. So for example, if you now take these models and perform a simulation using SNANA, what's the distribution of the detected parameters? So so over here, ejecta masses, the more the ejecta mass, the brighter the Kironova. So there are more chances of detecting them. The lanthanide rich component, the more lanthanide rich component we have, the Kironova peaks in redder bands. But since we are using ZTF, which is more on the optical side, you know, a lower lanthanide fraction leads to better detectability. And then this is something good, that this is a model that is parameterized by the observing angle. So head-on sources are better resolved, are better detected as compared to edge-on sources. And this is also the distribution of the detected redshift. So depending on your cosmology, you know, the prior on redshift, the injections that you do, they are uniform in volume, and the ones that you detect, you don't detect much at lower redshift. There's a peak, and eventually you don't detect it. So that's the detected redshift distribution. We also consider the models by Dan Kaysen et al. So these are also parameterized models. The parameterization is different though. It contains the ejecta mass, the velocity of the ejecta, and the lanthanide fraction. And this is already a part of SNANA. And the difference, however, is that there's no dependence on the inclination angle. One thing I did want to mention about the models is that while you know, at the first look, both of these models, they try to model the same physical system, but there is different parameterization, and oftentimes there is no one-one mapping between them. So for example, the ejecta mass is a common parameter, but then for the others, for example, the velocity of the ejecta or the half opening angle, you know, there's no clear one-one mapping between them. So it's not unexpected that there would be some model differences between the two. In particular, something that I wanted to point out is that, so here I've just plotted a Buller and a Kaysen model, at least by matching their ejecta mass value. So they roughly look the same. They peak at about half a day to a day in GNR, but then the decay time scale is slightly different between the Buller and the Kaysen models. For example, you notice that at the end of the 7th day, the R band in the Kaysen model is systematically brighter by about half to 1 magnitude, irrespective of you know, we have checked this with multiple values of the ejecta mass and stuff, but that's something that we generally see. Now, this is not a problem for Kironovae that are sparsely detected, meaning they have 2 or 3 or maybe 4 points on their light curves, because then the light curve is not detailed enough to select one model versus the other. But in case of longer light curves, which is again unlikely because that it'll have to be very closer, that difference does show up. So what we do is we incorporate both these models. We don't choose one over the other. We put both these models into the training set, and therefore get these simulated light curves out. Now we want to simulate an end-to-end data set. We want to connect our light curves to a sky map. And for that, we start out with a binary neutron star merger simulations. We consider this. We consider the publicly available noise curves from O4 for LIGO-Virgo-Kagra. We also repeat this for O5. And then we do an ensemble of binary neutron star simulations. We find the ones that are detected, and we run the rapid localization code based on them. So that way we have a sky localization. But now to get the light curve information, we need to map our binary components to an ejecta mass. Now for that, what we do is we use empirical fits to numerical relativity results to get the ejecta masses. So these are fits that are something like this. So if you provide the component masses, if you provide the compactness of the star, you get the ejector mass out. Now, the fit that we use is by Dietrich and Vivek, which has been used in LBK collaboration work before as well for GW 170817. So we decide to use that. Here I want to mention that since these expressions like these, they depend on the compactness of the star. First, let me mention why it depends on the compactness of the star. So depending on whether the equation of state of the neutron star is stiff or soft, a stiffer equation of state will lead to larger ejecta and therefore to brighter Kironova. So there's that correlation. But then we know that very high, very stiff equation of state are not supported by data. And here we make a choice. We choose the APR4 equation of state. And that is something that's a model equation of state that has high evidence from GW 170817 data from tidal deformability measurements. And so that's a choice that we make. But however, I would like to point out that if you restrict to the equations of state that have high evidence from the tidal deformability measurements of GW 170817, then this expression is not a very strong function of the compactness then. So that way our choice of one is just justified. And then we obtain the viewing angle which the Buller models depend on directly from the gravitational wave simulations. And we know that there is this distance inclination correlation because face-on sources are seen out to farther distances than edge-on sources. And that is something that naturally shows up from our gravitational wave simulations. We take the inclination angle and we can feed it to the Buller models. Of course, for the Kaysen models, we don't have the inclination angle dependence, so that does not come into play. And so at this point, what we have done is we have a set of merger simulation binary neutron star mergers. We have the sky localization. We have connected it to a Kironova light curve, and then all that is required to do is that doing the simulations for the other types of objects like type 1As, core collapses, tidal disruption events, superluminous supernova, using the same observing schedule. So we do that. And at the end of it, our total data set for training looks something like this. So we work with about 7K detected kilonovae, both Buller and Kaysen combined. And so here I'm once again showing the detected redshifts of the two, and they are not very different, which shows that the models are pretty similar, but then there still exist minor differences between the two. And then, as I mentioned earlier, we associate each of these Kironova with the sky localization. We do this for both O4 and O5. And then we need to select the other objects. So what we do is we window on the merger time of the Kironova. So we choose a time window and pick out these other objects that have their first detection in that window. So therefore, it gives us these other objects, and we rank them based on the SCiMMA probability, and we select the top 10 from those. This number 10 is once again, it's just a choice. One can, bump it up, and it leads to a larger data set. Although I want to mention that as you rank it, the chances are, if you go too deep, you'll get these objects which are farther out and potentially not even associated with the Kironova. So I think a choice of 10, we found it to be pretty sufficient. And therefore, our total training set contains about 70,000 light curves, 7,000 Kironova SCiMMA combinations. And now for each of these objects, we have the line of sight probability from the sky localization. We have the angular offset from the mode of the SCiMMA. And we also have, say, a localization area like the 90% localization area, all of which we can now supply as contextual information to sort of guide the classifier into filtering out the Kironova from the others. And then we do a 60-40 split for training and testing. Okay, so I did mention earlier that the original RAPID architecture used a gated recurrent unit network. So that has been changed now. So right now we use a temporal convolutional neural network. So here the basic structure looks something like this, and it's the main difference between a general convolutional neural network and this is that you notice how the output at time t is only convolved with inputs which are at time t or before. So this network is naturally causal, and features like the rise of a transient with time or a fall of a transient with time, and those time scales are well suited for a network like TCN. And then I also wanted to talk about these dilation layers, so these hidden layers, which are essentially capturing the features of different time scales. So for example, the d=1 layer is connected to every other one. The d=1 layer is connected to all of them. The d=2 layer is connected to every other one, and likewise. So here, as you increase your dilation layers, you are basically picking up features corresponding to longer times. So currently, this is the architecture that is used in RAPID. For LSID, we don't need very long time variations, and we find that only 2 dilation layers work the best. So therefore, the input matrix for RAPID for LSID, I'm sorry, is the flux error, the pass band. So that combination is the temporal information. And then you have the line of sight probability values based on the SCiMMAP, the angular offset, the 90% sky localization, all of which stay constant in time, but they provide the contextual information. Okay, so here I'm showing the confusion matrix from training the data. Once again, we only have 2 classes, Kironova and other. And here we notice that our Kironova class is not really does not really change that much, because most of our Kironova have very sparse observations, and therefore it will be the contextual information that will guide the classifier. That just like the redshift information that I showed in the very first slide, it sort of guided our classifier into deciding that this was a Kironova versus the same thing is true over here. However, you do notice that for the other class, the purity sort of goes up with time, and that is where the photometric classification is coming into play. So initially, it may so happen that a different transient, say a tidal disruption event, is coincident on a very high density region of the SCiMMAP. So your prior knowledge would be to call it, or the classifier will call it a Kironova to begin with, but then as time goes ahead with the photometric information, it will drive that down and eventually, come to the, it'll go down to the right class. And over here, I'm showing the ROC curve. So what we see is that by almost about 3 to 4 days, the curve is almost a right angle. Okay, I think I'm going to go over some examples now. So over here, the same notation holds true. We denote the true position of the Kironova by a big cross. The SCiMMAP probability is shaded here, and then blue circles are the other objects. So naturally, in a case like this, we see that the Kironova is pretty consistent with the sky localization, so it'll be given a higher score. So this is what we find. So you have the Kironova, so this is what we want. It has only one observation in G and R, so you might think that, well, that's not enough, but just because of its correlation with the SCiMMAP, it's given a high Kironova classification score. And the same thing is also true for a tidal disruption event, which may be one of these two. I don't know which one, but one of those that is consistent with the high probability region of the SCiMMAP. So in this case, the classification probability starts out from a high value, but as soon as more photometric data starts to come in, the classifier is able to assign it the correct class. And then as we move out to lesser dense regions of the SCiMMAP, if you have transients there like this type 1AX, then right at the outset they'll probably have a larger other class. And then as more data comes in, it'll go over to the correct class. Here's another one. So here we have another Kironova very consistent with the SCiMMAP. So in this case, the contextual information is sufficient by itself to distinguish between the Kironova versus the rest. So here we find that the Kironova it starts out high because of the contextual information, it stays high. And for the other objects, it starts out high on the other class and it only goes higher based on the, sorry. Okay, so here is an example where I am showing a more challenging case where you have a SCiMMAP, but then all of the objects over here are at pretty much high confidence regions. So over here, almost for all of them, the contextual information will say that this is a Kironova to begin with, but then you will rely on the photometric data to do the correct classification over here. For example, here is the KN that and the classes correctly goes over to the correct value. Sometimes due to lack of photometric data, there may be some ambiguity. Type 1AX, for example, this one, there is still ambiguity, but that is something that we have to live with. So in this case, the classifier would have filtered at least 2 out of these four objects. I just wanted to pause to check if there are any questions or not. I feel like I'm going really fast. So Adam, I'm not taking a look at the chat.
Not okay. Gautham just wrote something. As you can gather from that one piece of contextual information, we're having some energetic through the transient weather here in Urbana-Champaign. That was the noise that just I don't know if you heard it, Deep, but there was a huge clatter of noise from your end. That's what that referred to.
Sorry, that was just the thunder. There's a thunderstorm going on over here. Sorry about that.
No problem.
Is the reason that the 1AX comes up so often just because they're faint and they fade faster rather than like 1As or something like that? Is that why they get mistaken more?
Oh no, so it's not. I feel like, so in this case there is not enough photometric information. You see that it has been so the first detection is at almost, say, close to the limiting magnitude. But then there are other examples where a 1AX has been correctly classified. For example, this one, where there is more photometric information. But yes, if there is enough photometric information, then eventually the classifier will classify it correctly. In this case, for example, there's only like 2 or 4 data points over here, and that's why maybe if there was another one, the classifier would have gone down, but at least not from just the first 2 epochs of observation.
Okay, and there's a number of questions now. Heinz-Bernd asks in chat, says, I'm confused. The 3D SCiMMAPs that come with LVK real-time GW alert triggers do have a distance estimate at each sky pixel, and then are you using that in your proposed method?
No, not for this case. We are only using the line of sight probability.
Okay, and then Dave Sand has a question.
Hi, Deep, thanks. Do you ever do one of these simulations without putting an actual kilonova in? And do you ever decide that some other object then is an actual kilonova incorrectly?
So all of our simulations assume that there is a kilonova and then there are other objects as well. If there is no kilonova, it would be pretty much like considering the case, say, this one was not there. And then you would have, only the other objects getting classified. But if you're asking whether this can filter out other objects, in the absence of kilonova, yes, this can. All this needs is a sky location, a sky localization, so a sky map, the location of the object, and the photometric information.
It does seem to me that in the first 2 or 3 days, we're still in this case where we're going to want spectra of all these things, unfortunately. Am I reading that wrong? Like the kilonova classification is high for many objects in the first 2 or 3 days. Do I understand that right?
So that is because, so depending on, so over here, of course, I mean, sorry, could you, so my take is, as you are taking data, if you take more denser data over here, then of course, your classifier will converge quicker. Over here, we have very sparse data. So, I mean, you only have data taken in, maybe the 2nd day and the 5th day. And so therefore, your classification will only change when you get a next data point. So I don't know if that answered your question, but
that answers my question. I'm just asking. It just seems like the kilonova classification is favored for the first 2 or 3 days for many objects.
It will be because they are at high probability regions of the sky map, and
so that's what drives it. Yeah. Okay. Got it.
Yes. So
yeah, Dave, just to expand on this answer just a tad. Remember, we're only picking the top 10 objects to consider here, so they will necessarily be close to the high confidence region. But the thing is, the same filter has actually removed everything else that you see in LSST, and we get 10 million alerts per night from LSST. So even if you were to consider something like the 90% confidence region, that's still a huge amount of filtering that's happening.
Yeah, I mean, it's just that if you went down that, so if I went back a couple of slides and we selected, say, 20 objects instead of these 10 objects, we would have objects maybe around this part of the sky, which are naturally ruled out. But it can definitely be done. We are mostly focusing on objects that would definitely be confused with it being a kilonova. Yeah. Thanks, Gautham. And then,
so Deep, we have a whole stack of questions. People with their hands up. Would you like to work your way through them now?
Sure. Yeah.
Okay. So next up is David Kaplan.
Yeah. Thank you, Deep. When you're talking about contextual information, I'm a little confused about whether you're considering the gravitational sky map and its associated distance only, or if you're also using, say, host galaxy information, whether it's purely photometric or auxiliary spectroscopic information, because obviously in some cases those will match and in some cases those won't.
Yeah, so in this case we have not used a host galaxy correlation. We just purely assume only photometric information, so just these light curves and their location on the sky, what their line of sight probability is, what their distance from the angular offset from the mode of the sky map is, and what is the 90% area of the sky map. So only those features go into training this. But I mean, in principle, if we did have a very good handle on the host galaxy correlation for kilonovae and also for all the other types of objects that we are simulating, then that could definitely go into these simulations. In fact, one of the grad students in our group is working on building this host galaxy, the host galaxy correlation information that we can then pass into SN-ANA, but that's not quite ready yet. So as of now, that's not used. Yeah.
Okay, thanks.
Okay. Right.
Yeah.
So there's 3 more questions, and then obviously we'll we'll only have about 10 minutes left after that. So,
okay, can I just go ahead and finish my talk then?
I think that might be best. So Shreya, Igor, and Aaron, is that okay if your questions come at the end?
Yes, of course.
Okay, cool.
Okay.
Let's see it. Go ahead.
All right. So then I wanted to point out a different example. This is very rare, but can happen. So you have the sky map over here, but the true location of the kilonova is actually diametrically opposite. If I had removed these couple of points from over here, you would have noticed a small amount of shading over here as well. But it's possible that this antipodal correlation is definitely possible. But since cases like these are also part of our training set, we do get, once again, a higher classification score only from the contextual information, even in this case. So here is the kilonova, which is 180-degree opposite. And then the other objects which are near that, they also end up getting a high score, but eventually, if there is enough photometric information, then that would drive that class down. All right, I just wanted to, I'm nearing the end of my slides. I will talk about the performance on GW1700817. So this is the only object that we know of where we have a sky map and we also have a light curve. So the identical procedure we can follow. So here is the data from DCAM. We use the sky location probability, line of sight probabilities, etc. We pass it into this train classifier. Note that the real data is definitely not a part of our training set. And then we note that just from that contextual information, automatically we get a very high score and it's driven to higher values. And this is independent of the instrument that took the data. So in this case, HST, we use 475 and 336 for RNG. We get the same result for LCO and also for SWOPE. So just looking into the future, the next steps are integration with brokers, running this as a service. So the idea would be that in the future, LIGO sends out the sky maps, probably ZTF or LSST, which starts finding those targets, would send out that photometric information, and a tool like LSIT can be running in Antares, which would be doing the necessary annotation, characterization, ranking, and possibly communicating with the TOMs and downstream brokers to do the scheduling of the telescopes. Another avenue is plastic version 2, which is an effort that is being led by Gautham and others. So here, the idea is to stream mock alerts so that annotation tools and services can be tested. And since we have this mock kilonova alerts plus the SkyMap combination, we could do that. And of course, as and when more kilonova models become available, we should be incorporating them into the training set just to cover the entire space of models. We don't want to select any particular model because there's quite a bit of uncertainty there. And then we are also working on an extension over here with one of our summer students, Sai. I don't know if Sai is on the call today, but here the idea is that we have used one particular equation of state to do this kind of classification, but then thinking about the future when we have a sample of kilonova, then if we can build an archival tool that could possibly classify stiff versus soft equations of state just by looking at the photometry. And I just wanted to mention that that's, for example, a project that can be done with the SCiMMA Science platform. All right, so I'll quickly go over my conclusion slide. I'll conclude by saying that fast filtering is crucial when we look ahead, because we'll discover several factors, more transients that we see today. And contextual information can tremendously help in this purpose. And tools like LSIT can be incorporated into brokers. Fast communication, fast classification will mean quicker, judicious use of resources. And then the results can be used to decide the next, the following observing schedule. And then and science platforms, data lakes would be crucial to build and test tools like this, and that's maybe something that SCiMMA can provide. Thank you.
Thank you very much, and we'll go straight into questions. This is very stimulating. Shreya was first, I think.
Hi, Deep. Thanks a lot for your wonderful talk. It was really interesting. I had two questions for you. So one was brought up earlier. So I know you placed a cut choosing the 10, like the 10 transients within the highest probability region, I believe. So have you looked at like doubling or tripling the number of false positives, because of course in ZTF and other like LSST, we will have many more transients that would fall within high probability region.
Right. So right now we are only working with about 10, and the reason I think it's justified is because naturally things that are more farther out are further down-weighted by just being this correlation with the sky location probability, the angular offset. They would be down-weighted. So that's the natural answer, but we haven't tried increasing the data set yet, but that is something that can definitely be done. We have the infrastructure set up for that.
Okay, thanks. And I guess my second question was because it's challenging to figure out exactly at what point we should get photometric follow-up. And so in your, as you mentioned, there are sparse data points, and you're doing the classification based on that. So from your study, have you seen that there's a particular time or phase at which it would be very useful to get a photometric point to improve the
Actually, no, that is not. So over here, consider, say this example. This example here, the Kironova is over here. It is caught at close to maybe say 20th magnitude, which is already very faint. You don't have next epoch of observation. But then the idea is that if you have an example like this, then just from the contextual information over here, it would be a motivation for maybe other telescopes or maybe ZTF itself to do something like a forced photometry to get the next few data points. The contextual information will also, if you just have one epoch of data, then there is nothing much you can do but only rely on the sky localization probability itself, because that tells you, say, if this were the Kironova instead of that one, then just by one data point, one would naturally say that, well, both are pretty highly likely because both of them are at high confidence regions. So in those cases, we need the next epochs of data to rule out that particular case. So that next set of observations, suppose you have seen a detection, and based on that you want to schedule future observations, that is more for so that's not what we focus on over here. The hope is that the TOMs can pick that up. So the data that is sent out by LSID, the TOMs can pick that up and then use it for scheduling. Does that help?
Yes, thank you very much.
Okay, Deep.
Can I expand on this just with one quick point though? The simulations that we've done here, all of them are, as the filters indicate, only with the ZTF MSIP cadence. And so I assume that once you have a LIGO Virgo Kagra alert, there will be a whole bunch of other efforts to go try to identify the counterpart happening at the same time, and other surveys taking data. But unless that data is actually made public and put into systems like brokers through, say, SCiMMA's Hopscotch alert service, it's going to be hard to identify the counterpart using it. Those only go to private teams, right? And so this is in some ways motivation for teams to share their data, because you can make things faster, you can make counterpart identification faster, you can make spectroscopic follow-up faster, but unless you actually share the data, then you can't make a decision on anything to do that with.
Absolutely. I mean, and you know, this is the proof of that statement you made, Gautham. You know, the more photometric data we have, the better the classifier goes.
Okay, so we only have like 3 minutes till the hour. DP, are you able to stay on a little bit later to answer questions?
Yeah, sounds good.
Okay, excellent. So for those people who do have to leave on the hour, everything will be on the SCiMMA YouTube channel probably sometime this evening. So if you can't stay to hear the answers to all the questions, then you'll be able to catch up on them there. But next up is Igor.
Thank you, and deep congratulations for such encouraging results. It's really nice. I'm thinking about the practical use of such tool. First, I completely agree with what Gautham said earlier. It can really help with filtering out a large number of transients, especially in the Rubin Observatory era. I'm thinking how well this can do also in helping us distinguish Kironova from what we found to be by far the toughest of the contaminants, which are galactic CVs and some type of core collapse supernovae, in particular the shock cooling from core collapse supernovae. Are these type of sources among your others set, or are you planning on working more specifically on these ones?
No, that's a very good point, Igor. No, so yes, we haven't. We actually haven't included galactic transients in our training set yet. One of our postdocs, Konstantin Maranchev, he's working on an M dwarf flare. I know that M dwarf flares are also a potential contaminant, but then we also need to train our classifiers on, say, features like the offset from the galactic plane. Because there is a certain, because of course galactic transients would be living close to the galactic, you know, in the galactic plane. So features like that could be used as a differentiator. But to answer your question, not right now. We haven't. We have done this simulation mostly with. So this is the set of our other objects. Let me go back. So yeah, we have 1A, 1AXs, core collapses, 1BC, 91BG, tidal disruption events, superluminous supernovae. We don't have the galactic transients yet, but we do plan to include them eventually.
Great, thank you.
Yeah, I think next was Aaron.
Hi, Deep. Great talk as always. This is really, really cool. I wanted to ask a slightly annoying question. I might have missed you talking about this, but you know, like a very non-trivial fraction of gravitationally detected BNS mergers will have inclination angles lower than GW17817, and the lower the inclination angle, the quicker the non-thermal afterglow emission rises and the brighter it is. So I guess I'm wondering whether any of this classification has tried to inject rising afterglow emission onto the light curve and see how it how the classifier does.
No, we haven't done that. So basically, we just worked off the Bulla and the Kaysen models. So that is our model. We haven't done any more simulations on top of this. But if there are models that you know of that are publicly available, if there are SED models that can be easily integrated into SNN, and we could do that. In your question, or on your question about inclination angles, yes, we didn't do injections at specific inclination angles, but we did it uniform in inclination angles and distances in volume that is, and just from the fact that we started out with binary neutron star simulations, and that will naturally pick out, you know, head-on systems at farther distances as compared to edge-on systems. So that selection, that correlation is naturally there in our injection set. But the answer is no to your first question.
Yeah. Okay. I mean, that's really cool. I mean, maybe we should follow up offline, because there are public codes that can produce light curves and SEDs as a function of all of the relevant parameters, and it would be. I think it would be pretty easy to at least make light curves and SEDs. I don't know how easy it would be to feed them back into Rapid, but that might be a cool thing to do.
Thanks, Aaron.
Okay, so just as the next question is Sarah, but I'll just point out to Igor that Gautham has just written a partial additional reply to you in the chat window. Over to Sarah.
Yeah, hi Deep. So my question is more on the practice. So for the moment, you show results with a regular cadence and so on and so forth. And so you probably know that we are launching a campaign with citizen science following public alerts of ZTF using the filter that we have in France, whose name is Think. And so we are a bit working or struggling, I don't know, to find, in fact, the great alerts on ZTF to determine where they are Kironova, because our objective is to really focus on the first 24 hours, because I believe that even if the cadence is every 24 hours, they should have some punch, between the 24 hours. And that if you have amateur or collaborators around the world, you can have, data after 2 hours, the first point, after 4 hours, and so on. So in fact, my question is, since our colleagues and amateur astronomers are ready, how we can help you to try to improve your tool and to really more see in practice how we can better classify with more data, instead of waiting just for 04 and see if people are gonna share their private data to see a classifier.
I think one important tool that would be really helpful is actually the observing schedule for the different telescopes. So here, we do it for, we have just selected these. We have gotten, not me actually, but one of our postdocs, Konstantin Malanchev. Konstantin did a wonderful job of collecting all the ZTF data and then building this this observing schedule out of it. And also giving us the getting the efficiency function. We had to estimate it from the publicly available data. So I'm sure if there is if other teams could provide their observing schedule, what observing schedule they would follow, to what depths they would go when there is a trigger, that could be a very good. This sort of ties back to the question that Igor asked, that in terms of practicality, and something that Gautham said, that the observing schedule changes a lot when you do have a trigger. Telescopes see deeper, so having those at hand will be a very useful thing to train these kind of classifiers on.
Yeah, well, may I jump in again? The question is a bit about cadence, but it's also about follow-up on transient. And so it's more about how much resources you put. Do you ask people, for example, to go as deep as ZTF, for example, 21 magnitude? And do you need like 10 additional points? This is this kind of, the resources are okay. It just means how you handle that. So you can have other cadence that you want, etc., etc. But it's more about evaluating the resources that you need at minima to obtain a good classifier, and not triggering spectroscopy, for example.
Yeah, so in some sense we are limited by, so for example, if we do have very few points, then it is, that's all that you get. It's only a result out of the contextual information that we get. So now it's really up to the teams. I feel that if they do get a situation like the following, would they rather spend the resources to maybe get the next data point quickly? I don't know, Gautham, do you have a better sense to answer this? I'm not sure if I'm doing a very good job at answering this.
So my sense is actually it's hard to get, especially if you're using amateur facilities, to 20th magnitude, and it's really hard with small aperture telescopes. You're not, you're talking like 16-inch and more at that point if you really want to try to go to those depths, and there'll be fairly long exposures of that. More to the point, you actually benefit a little bit by being a little patient and waiting, because the Kironova is getting brighter. So the sort of survey mode of operations where you know there's another image coming the next day is fine. And what people should do, I think, is take the initial output here, use it to sort of make a rank ordered list like we've done of potential counterparts. And for facilities that so most of the cases that you'll see actually are cases where the Kironova will be pretty readily identified, and the other class gets to a high value or is already higher than the Kironova at the beginning. So maybe take like 1 or 2 spectra and then just wait if you haven't identified a counterpart, because you will get another point and then the classify will become more certain. But trying to throw smaller aperture telescopes at this problem with amateurs and such, I think will really upset and annoy people. I think it's much easier in the amateur game to play the game of supernova discovery, and there it's been tremendously successful over many, many years. I think amateurs led the efforts to sort of really find the low-Z sample of supernovae, but kilonovae are fainter, harder to follow, evolve faster, and I think we will frustrate a lot of amateurs if we're sort of asking them to do it.
Well, thank you. Well, we just made a program about this, so I'm happy to show that they are interested in that.
Yeah, and if there's a whole bunch of folks with 1 million telescopes and nice imaging cameras that do want to connect up with Hopscotch and Treasure Map and some of the other services that we're deploying in SCiMMA, then absolutely let me know. But I think there's a range of amateurs with everything from 80 millimeter telescopes all the way up to like absolute monsters, and so the subset of people that I think can really make a difference here is not quite everybody, and so we do want to be we do want to set realistic expectations going into this. I think particularly when you're involving the public, that's really, really important to do.
Okay, so I think, assuming Igor hasn't raised his hand again, I think it's just up from before. Andy Howell has the last question.
Hey, yeah, nice work. And I was just gonna say about the sharing of photometry. Of course, well, I was wondering how you're expecting to get photometry from people, and I guess maybe Gautham kind of answered. Maybe that's why we need Hopscotch. But we do need maybe another module or something to decode people's photometry, because some people are going to have Sloan stuff. Some people have different filter sets, like Atlas has an orange filter, and then some people have Landolt photometry, B and V. So I would encourage that to be on your future work, some kind of thing for decoding that. And then the other thing is, who's going to be running this? Are you going to run it as a service where you take everybody's photometry and do this decoding and put it all together? Or are you leaving that up to each individual group? Yeah, maybe I missed this part here. So that would be good to see. And also I highly encourage you to use the distance information available from LIGO and any other, I don't know if you were using other contextual information like host galaxy type, and mass, but those kinds of things. So.
Yeah, the last question first, no, we are not using the host galaxy type or not. The host galaxy information is not still not there in our simulations, but then it can be, so that's definitely a nice future direction. In terms of running this as a service, what we were thinking, we meaning myself and Gautham were thinking that this would be hosted in a service like Antares. And in terms of different instruments providing the data, so there, of course, we need to probably consider, training sets where multiple observing strategies from different telescopes are actually combined together. It is possible to do that using the framework we are using. It's just that we haven't done that yet. I don't know if that answers your question, Andy.
Yeah, but I think it's very important. This is going to take a long lead time to develop. Combining heterogeneous data sets is not super easy. And so if we want something for 04, I would start now on that component of it, because it's akin to doing a K correction where, you know, you just have everybody's filters and then you have the SED and you can put the data together, but it's not trivial. So, and you could test that with people's existing published data on, you know, the first Kironova, because it's a wide variety of filter sets and calibrations and everything else. This is one of the things we were really worried about in writing the first paper. One of the reasons we wrote that first paper so fast, we did not include light curve information, because that putting everybody's information on the same system is such a hard problem that that's a whole research project in itself.
Mm-hmm.
So Andy, if I could take a quick stab at this as well. This is why within SCiMMA and these discussions with you and Mario, I've certainly been pushing for a fixed schema for the hopscotch service, so that, you know, filters and such are reported in a standard machine readable format that can be parsed. And then I think the K correction issue is a little bit overrated for this, because these are all low redshift objects. The filters, yes, they are different, but for the most part, people are using things like Stone, and if there are a few notable exceptions. We have SED models for these things, so we can do an S correction. It's not a terribly large thing. And more to the point, what you saw from Deep's earlier slides, applying this to GW 1708-17 data from DECCAM, HST, SWOP, and whatnot, is that without retraining Rapid, despite the fact that these filters are actually different, it still seems to work reasonably well. So for classification, you're okay. For physical inference, you certainly need to do a better job. And there I completely agree with you. But, you know, if our goal is discovery initially in our entire cyber infrastructure, we don't have to worry too much about the K correction or S correction aspect of this. And yeah, I think the only way to get people to play nicely in this world and share data so that everybody can benefit is to use services like Hopscotch and report their measurements on things like Treasure Map, and coordinate follow-up with things like DOMS, which of course, all of which you have been part of. It's I think, going to take a little bit of a cultural change, but my sense is, looking forward to LSST and 04 and 05, we're going to find so many more of these things that, you know, there's enough objects that we will not have to fight over them in the same way as GW 1708-17, and it behooves us to cooperate and collaborate.
Yeah, sorry, I missed that bit. I mean, over here, clearly, I mean, I've just taken the data out of the Open Kironova catalog. There are no K corrections applied to any of these. Like, I've just taken the data as is and put it in.
Just to be clear, I don't think you need a cross filter K correction. Redshift matters. All I was saying is basically what you think of maybe S corrections. We never call them that. We always call them K corrections, even though, so that's just a language difference. All I mean is, you're going to want to be, if somebody has B and V Johnson calibrated, Vega calibrated data, you're going to want to be able to incorporate that. You're going to want to incorporate Atlas data with very different filters. So just don't leave that part undone when it comes time to, and then you can only use Sloan filter data.
Got it.
Okay, so Patrick Brady has his hand up, and this will be the end.
Just a quick sort of reaction to Gautam's comment about standard formats for sharing information. The way I think about the service like Hopscotch and that question is they're actually independent. Hopscotch can carry any container whatsoever, and therefore, you know, it could be completely something that can't be parsed by anyone except some special team. But so the question I think that I'll put to the group on the phone, and, you know, how do we move forward on it, is forget connecting it and making it a default container for Hopscotch. How do we address the question, Gautham, that Andy and Gautham raised about having common shareable information that can be used? Where do we start with that? We don't want to go into, I think let me phrase this in the affirmative. There's sort of prior art on trying to get standard formats for things through VO, and clearly that's something that we should look at to know if there's something there already that can be used for it. But if there isn't, it seems like now would be a good time to kick off defining a format, writing a minimal library and beginning to work together on how to put that data together and have an easy, common, usable tool. So where are we on that? Any reactions to what I just said?
Aaron has his hand up as well.
Yeah, I just want. Go ahead, Andy.
Okay, well, I was just going to say, Patrick, yes, I'm working on that in the sense of trying to put together a team of people who are interested in this to come together to define a format, to look at what's been done before and to say what changes need to be made. And I have a spreadsheet started of names, but it's a good reminder that I need to send out the emails and try to recruit people to be on this committee.
Yeah, I just wanted to say that, to echo what Patrick said, I think it's a great idea. I think one of the things to be careful of is, as you mentioned, Patrick, there do exist this methodology for making standards in the community through things like IVOA, but that takes, a decade. When we were building Treasure Map, we purposefully did not do that. And, we had a bunch of conversations about this, and we're like, well, who are we to choose a format and a standard for the community without, going through all of this, sort of fact-finding missions and all these meetings. And at the end of the day, build it and they will come, and then you can always change it. That's my perspective. So, you send out an email and you get people together, and then you just start building something. Yeah, anyway, that may not be the most politically correct approach, but I think it's the one that works.
Yes,
Go ahead, Andy.
Oh yeah, I agree with Aaron much more than the IVOA approach. So, but I also I do want it to take into account people's use cases that I have not thought of, and so that's why I'm going for a minimalist committee of people who will not just pontificate forever, but who my plan would just be to write out a straw man argument of here's the way I think it ought to go, and then have people tweak that and poke holes in whatever I come up with.
Yeah, if I can just add.
Go ahead,
Gautham.
I mean, I'm in complete agreement with Aaron and Andy here, and I think the thing to do here is, look at what TNS has done, what sort of information can be submitted there, not necessarily the textual information, not the comments, but just the form and the structure. And I know people have their issues with TNS, but it has sort of got a homogenized structure for how data is submitted in. And I think minimally we have to capture this. So if we start there and then circulate it to a broader community than the people on Andy's spreadsheet, the LSSD science collaboration, for example, plus LVK, IceCube, I think we'll get some useful feedback. We can tinker with this, and then, like Aaron suggested, don't try to make it a standard, make something useful, and then they will come.
And it doesn't have to be everyone that comes, right? It just has to be the people for whom it's useful. So
yeah, my thinking right now is to actually make a format that is dynamic, that you basically establish a sort of standard set of tags or whatever, but users can add tags, and as long as you publish them, it's sort of like a database schema. As long as you publish what you're transmitting, anybody can look that up and then decode it. But that's just my thinking, and we'll see what happens when I get other people involved.
Yeah, and I guess I want to just iterate. My statement here is I do think we have to be aware, and we cannot ignore the existence of IVOA or other practices, and that would be a bad thing to do. On the other hand, I fully agree with the attitude that at some stage, if the solution doesn't exist today, and other groups have been thinking about possible solutions for many years, but just haven't got it in place, then the best approach is to bootstrap a solution quickly. I do think, though, I'm going to say this is my sort of, I say this repeatedly, I'm going to say it again. I think that a format without a library is useless. And so I would actually say that Andy, from my perspective, I think sure, the quick document with a quick sketch is a good idea, but I think a very public and open project on developing a library that follows the format would actually get the most traction the most quickly. And I know that's a tendency for your group and others and Aaron and so on. So it's great, but I definitely encourage it, and I think it'd be fantastic to move that along.
Yep, 100% agreement.
Okay, so I will seize the moment to finish on agreement. That was a really interesting discussion at the end there, and something we need to concur on carry on having with the community as we get our messaging system to being a sort of production reality, which is fairly close now. So thanks again to Deep, and thanks also for your patience in hanging on past the hour. And we will be having another public telecon, or we plan to have another public telecon next month in July, and a notification will be sent around about that. So thank you to everyone, and thank you particularly to Deep.